So let's talk about a property of light called refraction. Refraction really means the bending of light. This makes the waves of light change direction. Have a careful look at the glass of colored water in the picture. Particularly, pay careful attention to the drinking straw. You'll notice that the straw appears discontinuous. The straw appears to be broken in two, and the two ends don't seem to meet. This is obviously not the case, but it's an example of the refraction of light. That's because as light moves through space, it travels at a maximum speed of 300,000 kilometers every second. But that's its speed through a vacuum where there are no particles to slow it down. The thicker the particles are, the slower light waves become. And as they slow down, they change direction a little bit. So the waves that have to travel through the glass and then through the water actually change their direction. They bend a little bit in response to being slowed down by all of those extra particles. That's in comparison to the waves that are traveling through the air, which is much less dense. And so the air particles slow the waves down less than the water particles do, for example. This bending of light makes it look as though the straw has been cut in two by the water, when it really actually hasn't. Let's take a look at the refraction of light in much more detail. All right, rules for refraction are a little bit more complicated than the rules for reflection. If we have a fast medium, which is not very dense, so that might be air, for example, and we compare that with a slow medium that is more dense. Now, this might be glass, for example, or water. But in this case, with this rectangular prism that you see drawn on the screen, we're really talking about something like a very clear, high-quality glass. The incident ray is the light ray that approaches the surface of that slower medium. Now, we can draw a normal to the surface of the glass block, the same way that we did when we were drawing normals to the surface of a mirror. It's an imaginary line that forms a 90-degree angle with that face that the incident ray is striking. Next, imagine if the incident ray traveled on uninterrupted, with its direction unchanged. That's what this short dotted blue line represents. Our picture of, in our minds, of if this incident ray did not change its direction, if it did not refract. But in fact, that's not the case. And instead, the incident ray changes its direction just a little bit. Notice that it's got a little bit closer to the normal than it would have been if it hadn't been bent at all. And this is the path that this light will follow as it travels through this dense but transparent material like glass. Then it reaches another surface where it's going to pass out of the slow medium, the glass, and back into a fast medium like air. And the opposite thing happens. We first of all imagine a normal line forming. And we, in our mind's eye, picture that, that ray passing through the interface between glass and air without changing its direction, without refracting. However, we know that in fact it will bend, it will refract. And so the refracted ray that passes out of that rectangular prism actually moves off in a direction that looks a little bit like that. Okay, so that's how refraction would occur through a rectangular prism made of glass. Here's a couple of rules for you. When a ray passes from a fast medium into a slower one, as it did on the left-hand side of the diagram, the rays will bend toward the normal. So from fast to slow, rays bend toward the normal. And the opposite happens when the opposite is true. So when the rays pass from a slow medium to a fast one, the rays will bend away from the normal. Study that diagram really carefully and get it copied very neatly into your diagram. You want into your books. You want to be neat here. The more neat you are, the more sense it will make when you're studying. Okay, now if we use a triangular prism instead of a rectangular one, that actually doesn't really change much. Exactly the same thing happens. Here's our incident ray. Here's our normal, which is a 90-degree angle to the surface of the prism. We imagine what would happen if our incident ray didn't bend, but we know that it will. We know that it's going to bend toward the normal because it's moving from air into glass, from a fast medium into a slow one. And then when it gets out to the other side of the prism, it needs to move from a slow medium to a fast one. So again, we draw the normal. Remember, the normal is always 90 degrees to the surface of the prism, the same way that it was always 90 degrees to the surface of the mirror. We imagine the line being unchanged, but we know that in fact it will bend away from the normal. And that's an example of a pathway that light would follow if it was passing through a triangular prism.